through it. All right, so we are talking about chapter 7, which is the radiology imaging. Oh, you got to be kidding me. It's not working. All right. So these are the objectives. You can go ahead and read. For chapter 7, I removed a couple of things out of that chapter. It's because it's a little bit more in-depth than I would like it. However, I am going to touch on certain subjects that are related to the things that are on the PowerPoint. So let's talk a little bit more about image production process. Once again, X-ray was discovered in 1895, which was on your test, and I hope everybody got it right. Okay?
I'm joking.
All right, so we need an X-ray beam. For us to produce an X-ray beam, we need what we call a high voltage to create electricity. This X-ray beam will go ahead and pass through matter, and through the matter, it will strike what we call IR. IR stands for image receptor. Okay, not interventional radiography. Okay, so when I say IR, I'm talking about the image receptor. The image receptor will then convert the X-ray beam into electronic data or a data set, and then it turns into a signal, and it will pop up on the image displayer. So where it talks about the electronic data, so because we have stopped from film all the way to digital, all our images are now in a digital form. So the image process, we don't even talk about going into the processor room, dipping the film in the chemical for the image to pop up. We go straight into digital, and we got away from the film because it was taking so much exposure to create image, and it was giving patient a lot of dose, and productivity was really, it was slowing down productivity. And we want more volume of patients, therefore we have to go ahead and transition from film all the way to digital for us to get more patients, the department functions more effectively, and it's less stressful for technologists. I think PIH. Anybody plans on volunteering at PIH? You did already?
No, I mean,
you will. Okay, so you will notice their equipment are so old. When I say it's old, it is so old that literally you'll be turning stuff like that, and that's great. I prefer to be trained on that kind of equipment because you learn how to use tech factors, which I will talk about in a minute. Tech factors are the factors or the buttons that we need to push to create the radiation or the patient dose, right? We choose those tech factors. Doctors do not. And those doses are really based on patient's body habitus. I did explain what body habitus is, right, last week. What is a body habitus? Body type, right? All right, so X-ray production requirements. So how do we produce X-ray? We produce X-ray in an X-ray tube, okay? It is like a vacuum tube. Why is it a vacuum tube? Because it has less air in it. If it has been degassed, okay? Degassed means it has been removed. We have removed all the gas, as much gas, out of the X-ray tube. And why do we degas this X-ray tube? We degas the X-ray tube so that we don't have an interruption of electrons not interacting with the anode side of the X-ray tube. So we degas it so that we can have a better interaction with the electron and the anode. By the way, this is the cathode side. This is the anode side. Okay? So this is cathode, this is anode. This is the negative side of the X-ray tube. This is the positive side of the X-ray tube. This here is what we call a filament. I will give you a whole a picture, and you're going to have to learn how to label all of it and learn the functionality of each part. I will go over it at a later time. But if you have the document, you can go ahead and look at it. This at the bottom part, that is where we create what we call thermionic emission. Thermionic emission, once again, it is the boiling of electrons. Okay? You look confused.
I have a question when you're done.
Okay. All right. So this is the cathode. This is the cathode side. This is the anode side. This is the physical structure of the X-ray tube. Now, if we have to go to the anatomic level, the anatomic level is where you learn how we produce X-ray beam. Okay? But this is the X-ray tube. And where do we create brimstone or X-ray beam? We create it at the tip of the anode tube. Oh, at the tip of the anode structure, which is right at the bottom here. Okay? I'll go over it when we talk about the interaction next week. So we have classes of radiation, right? We have the primary radiation, the scattered, the absorbed radiation, and remnant. Remnant radiation is a radiation that has passed through the patient that is reaching the IR. Remnant radiation consists of the patient information, which is also called subject contrast. Okay? This is being recorded, so you get to review it. So we have the primary radiation or the primary beam. The primary radiation is the X-ray that we created. Okay? Then we have the absorbed radiation, which I will go over the interaction. The absorbed radiation is called photoelectric absorption or photoelectric interaction. Okay? Then we have scatter radiation. Scatter radiation is a radiation that does not penetrate through the patient, but it exits out. It bounces off the patient. That's why I get those radiation. Okay? So as you can see, we have four of them. We have the primary radiation. Okay? It goes through the patient, and then it comes out the patient. It reaches what? The cassette. Now we have another kind of radiation that bounces off the patient because it wasn't strong enough to penetrate the patient. So this here will have what we call a long wavelength, low energy. Because if it was high energy, it will penetrate through the patient. But because it's not a high energy, it just bounces off the skin. So the wavelength here, when I start talking about the interactions, the wavelength here is very long. It's not short. The one that has the shortest wavelength is a primary beam, which is also called what? Brimstone. Okay? The one that is absorbed by the patient is called photoelectric absorption. You want me to review some?
You said the primary radiation was...
It's brims. This is what we create in the X-ray tube. This is brimstone.
Okay.
Mm-hmm.
And the wavelength is...
Oh, this one, the wavelength would be shorter. Because, so when we have a high energy, that means we have a very short wavelength. Therefore, it's able to penetrate through the patient. When we have a longer wavelength, it is low energy. Can we all agree on that?
Yeah.
Lower energy do not penetrate patient as much as a short wavelength. Okay? Therefore, if it doesn't penetrate through the patient, it comes out. This is why I get my radiation. I get scatter radiation because it don't penetrate through what? The patient. Any other question? Yes, sir.
It sounds like you're going to go next week, but I just want to check when the electrons hit the target, the plate, it's knocking an electron off of the tungsten molecule.
That is at the atomic level, and that's why I was going to cover it. Like, okay. You are absolutely, you are on the right track. You are right.
So if it's knocking that electron off the tungsten molecule,
it doesn't knock out an electron. No. You're talking about characteristics. So since you went there, I might as well just go there. So when we accelerate electrons from the cathode side to the anode, what happens is we have millions of electrons, right? Because we have millions of electrons, what creates brims is the electron that go by the nucleus of tungsten. It decelerates because the nucleus of tungsten is so strong that it slows down the incoming electron. However, we do have other electrons that interact with the outer shell of tungsten. So there is ionization that occurs in tungsten, but you cannot have those. That's called characteristic radiation. Brimstone doesn't ionize. There is no ionization for brims.
okay. So it's a deceleration rather than just a
Exactly, it's a deceleration. Any questions? Sorry, he went a little bit further, so I had to catch him up. We good? Yeah, y'all look confused, but I'll continue. All right, so let's talk a little bit about attenuation. So attenuation, I told you guys last week or the week before, what is attenuation?
It's the loss of radiation energy.
As it passes through what? Matter, okay? So as radiation passes through matter, it can either, as radiation passes through matter, the wavelength gets longer because it's passing through matter. If I don't place an object in front of a wavelength, it's not going to slow it down. But the moment I place something in front of a short wavelength, it gets to what? Slow down, because that impact is slowing down the wavelength. Therefore, anything that exits outside of that object is going to be what? Less radiation compared to the incoming. Okay? So when we talk about differential absorption, we're really talking about the absorption of radiation of the patient. Okay? It's just the absorption of the patient. We have high attenuation and low attenuation. So with high attenuation means we have something that we call radio opaque. Okay? Radio opaque is related to high attenuation. And this is like a terminology kind of thing. When you have a high attenuation, what is the definition of attenuation again? You said it.
It was the loss of radiation energy
Right.
that goes through matter.
Through matter. So if I said I had a high attenuation, what am I saying? If you're trying to connect those two, if I have a high attenuation, that means more radiation was absorbed, right? Attenuation is the decreasing of photons that passes through matter. Am I correct? If we agree on that, if I say I have high attenuation, that means more radiation was absorbed by that matter. See, you have to understand the definition really thoroughly for you to connect those two. I can repeat it again if anybody wants me to.
Yes.
Okay. If I have a high, okay, first of all, let's understand the definition of attenuation. Attenuation, it is the decreasing of photons that passes through matter. Can we all agree to that? So if I say I have a high attenuation, that means more radiation was absorbed through matter. Okay? That is also called radio opaque. Radio opaque is the matter or the object that absorbs that radiation. And this will make sense when I talk about the interaction with matter. And as you can see in this picture, this is radio opaque. The reason why it's white over here is because the radiation was absorbed by this material. Because there's no material here for it to be absorbed by radiation, it is called radiolucent. That is called low attenuation. Based on that definition of attenuation, I could tell you whether it's high or low. When an object does not absorb radiation, that is low attenuation. When an object absorbs more radiation, it is what? Radio opaque. So if you have to study this all over again, I really need you to understand what attenuation is before you move on, because everything else will be confusing. Yes, ma'am?
Can you repeat that last part about radio opaque?
Yes, radio opaque. So radio opaque is when an object absorbs a lot of radiation. That means we have a high attenuation. Okay? Radiolucent means the object did not absorb any radiation. That is low attenuation and radiolucent. Okay, so let's talk a little bit about tech factors. So we call tech factors as prime factors. Why do we call them prime? Because we can create radiation dose without these tech factors. So when you go to the hospital and the doctor say, hey, I'm gonna have you get a chest x-ray, the technologist needs to go behind the control console. Where they use this button or where they press this button, that area alone is called control console, because the technologist, this is their playroom, okay? So they have to go ahead and choose which mass they want to use, which is here. They have to use MA. MA is the quantity of electrons, people. Please remember that. MA is milliamperes. It is what? Controlling the quantity of electrons. Okay? That is the patient dose. MAS is the patient, MAS or MA, it is the patient dose. Okay? So on the test, if I ask you which one of these prime factors control the patient dose, what is the answer? MAS. So we talk about KVP. KVP, it is the kilovoltage that we need to accelerate that electron towards the anode. Okay? The KVP, its purpose is to penetrate the X-ray beam or the X-ray photon through the patient. Are we clear?
Can you repeat it one more time?
Of course. The KVP, its purpose is to what? Penetrate those electrons or the photon that comes out of the electrons or the photons that was created by the electrons. It's supposed to push it through the patient's body. Okay? So its purpose is penetrating through the body. The KVP, its purpose is to penetrate photon through the patient's body. That's yes, sir.
So the KVP controls the frequency?
No, it doesn't control the frequency.
Does it control the acceleration? Or no, the speed?
Okay, so you getting there. You're absolutely right. So we have KVP and we have KEV. KVP, it is the voltage that's associated with the electrons towards the anode, right? And the KEV, it is the energy or the photon unit that was made by the accelerated electron. So the KVP accelerate the electron from the cathode to the anode. Once they are decelerated, energy is released in the form of photon. That photon, if we have to measure it, guess what? It's KEV. That's why we say KVP. KVP is the peak of it, the highest energy that came out of those electrons that were accelerated. And this will make sense when I talk about the interactions. So the KVP, I just need you to memorize it as what? Penetrates through the patient, okay? Because it is directly related to KVP. Or KEV. Yeah. So SID. What is SID? SID is source to image receptor distance. We are saying from the X-ray tube all the way to the image receptor. The image receptor could be either the table or it could be the X-ray, the one that's standing up where you do a chest X-ray, your chest have to be on it. That is the image receptor tube. That's IR. So the source is from the X-ray tube all the way to the image receptor. I believe I have a picture right here. There you go. Well, I wanted to go further, but I couldn't go between her legs. But what was it? SID. SID is from the X-ray tube all the way to this board. That's how we measure SID. Are we clear? Yes, sir.
Are you referring to the wall bucket?
The wall bucket, yes. Yes. The wall bucket or the table bucket. That's the SID. Are we clear? Okay? SID is from the X-ray tube all the way to the what?
The board too.
The receptor. The wall bucket receptor. Yes. Okay? Because this will be on your test. You're welcome. And I don't think your book covered this, so I wanted to add this. We have what we call OID. OID is object to image distance, if I remember correctly. It is the distance between the anatomy and the wall bucket. Okay?
Body to the bucket.
Yes. So we have a distance from the X-ray tube to the wall bucket, and we have a distance from the body part to the wall bucket. Okay? And I will give you a formula for that. The formula for SID is OID plus SOD. Don't worry about SOD. I just need you to know this is a formula for SID. SID equals OID plus SOD. SOD will be source to subject distance. Okay? I won't give you a math problem of that, but I do need you to know it. Okay? So let's talk a little bit about image receptors. We do have what we call CR and DR. DR has two parts. See, with CR is made out of what we call PSP technology or plate. This is what the CR is. With the CR, once we expose this cassette, we have to take it to a reader. Okay? The reader will process it and then it will display the image. This is what we call CR. This is considered digital, but a different form of digital imaging. Okay? So in our department, in the radiology department, we have this cassette, and we have this, and we also have the reader. And we don't use it, but we like to show it to the students as this is what the CR is. There's so much physics. Your book go through physics of how it process and stuff like that. You don't need it for this class. Now we have what we call digital direct radiography. So with these kind of X-ray equipment or IR or image receptor, by the way, this is a wall bucket that got flipped in a horizontal plane. We are able to maneuver and manipulate our equipment and our IR in any shape or form that we want to basically help the patients out. And improvise with the patient's condition. So this is what we call direct digital radiography. Okay, so with this specific equipment, the only thing you do is remove what we call a grid. Don't worry about that yet. But this is considered digital. When we expose the patient's hand to radiation, the image pops up immediately. The other one, the CR, we had to expose the patient, walk to another room, and process the picture for you to what? Show. But with this, we don't have to. The moment we expose the patient hand, the image comes up what? Immediately. That's the big difference. Okay? Now we have what we call indirect. Okay? With indirect radiography, we do have the same concept as the previous slides, but the only difference is the cassette, it is digital and we don't have to process it. So this cassette, we can take it out and put it inside the wall bucket or the table bucket, expose it, and the image can pop up. It's called indirect because we can literally remove it and put it anywhere to do the image. The other one, we couldn't remove anything. Okay? I don't want you to know the physics of it, but I do need you to know the materials that each of it contains. Okay, there goes the math part. All right, so as I said before, when we talk about MAS, it is a prime factor. So how we get our pictures to be white, black, gray, it comes from the mass, okay? The mass is the quantity of X-ray production. I've said it many times, like 3-4 times, hint, hint, hint. Okay, it has a direct relationship, and it is a very simple multiplication. If I give you 300 MA, and I said the time was 2 seconds, what would be the MAS? 600. That's probably the most simplest math in X-ray. Okay, so I'll give you more homework of that. And this controls what? This controls what on the patient? Wait, somebody else said the dose. This is what gives the patient their dose. This is patient dose. Okay? So you can actually, if you ever go to the hospital, you're doing a chest x-ray, you can actually take, hey, how much dose you gave me? Just be curious. Hopefully they didn't use more than they need. But that's the mass. Mass, this is the patient, this is what contributes to the patient dose. I can't say that enough. Patient dose comes from MAS. Okay? So yes, this is an example of it once again. So the thing that may be a little bit tricky, and I will do to you, this time right here, I could put it in milliseconds. Okay? I could put 20 milliseconds and you will have to convert it. So yes, your homework will have that. So this law right here, it's called MAS reciprocity law. It's telling you it doesn't matter what number, or it doesn't matter the MA and the time. If I get the same value, it is what we call reciprocity. Okay? So for example, I have 400 MA and I have 0.04 seconds. I got 16 MAS. But guess what? I could do 200 MA and I could do 0.08 seconds. I get 16 mass. It could be either or. As long as I get the same value, that is what reciprocity is telling us. Now you're probably wondering, why would I change it? Depending on the exam that I'm doing, sometimes I need more time than I need mass. But because we know MA consists of the patient dose, I want to limit how long the exposure is going to be for the patient. So reciprocity, all you need to know is reciprocity tells you it doesn't matter the MA or time as long as I have the same value of two different tech factors. Is that clear? You good? Okay. So yeah, expect homework. All right, so when we talk about tech factors, as I said, this is the tech factor that actually creates this kind of image here. Depending on the structure, depending on what's going on with the patient or the procedure, depending on the procedure, depending on the exam, this is a classic example of what we call attenuation. This is what we call a dye. When the patient drinks the dye, it will increase attenuation. What is attenuation again?
Absorption.
Absorption. So if we are able to see the structure clear, that means the dye that the patient drank has a high attenuation. It absorbed more of the radiation. Therefore, the structure is more clear. Okay? Attenuation occurs a lot in fluoroscopy. Questions? Y'all look like y'all got a lot of questions. Ask people.
Okay, so in this case, low attenuation
Uh-huh.
was presented, so you guys put a dye in there so it could present high.
High, exactly. So if I had shot a regular chest X-ray, I won't have all these white stuff.
You would just have like the spine and
Exactly. I would see the colon, but it wouldn't be this bright. That would be low attenuation. But the moment I add a dye to the structure, now it's absorbing more, which means it is making the structure more brighter. I can see I can see clear definition of the structure, its curvature, and everything. That's why we use that. So this, if I put this picture on the test and I ask you, is this a high attenuation or a low attenuation? What you gonna say?
high.
Okay, so if I ask you, is your structure high attenuation or low attenuation?
That would be low.
Thank you. Good job. You just took your test. Look at you. All right, so patient thickness, and the part that we are shooting plays a huge role in what? Attenuation. Okay? And the pathology plays a huge role too. So once again, MAS is the quantity of what? The X-ray photon. KVP is the penetration or the beam quality. This is the term you will hear from every program, at least once. The KVP is the beam quality, and its purpose is also to what? Penetrate. Okay? It has direct relationship with signal value. We are talking about the digital aspect. Because depending on the penetration, if I have digital signal, which is a whole different... just ignore, cancel this part out. If I explain it, I will have to talk about the whole digital and the physics aspect, and I don't want to do that to you. So our X-ray beam can be heterogeneous or heterogeneous. What is heterogeneous?
Straight.
Well, not in a sexual preference, but so heterogeneous it means there's two types. Okay, it could, and this you probably will be happy. It's either long wavelength or short wavelength. That means the X-ray photon that we create in the X-ray tube that is coming out can be two things: long wavelength or short wavelength. That's what it means by it's heterogeneous. Are we clear on that? Because the photon can only be two types of wavelength. What? Short or high. So when I explain how we create BRAMPs next week, you're going to be like, oh, hopefully that's what you do. But yeah. Any questions about this? We good? You sure? Yes, ma'am.
Can you repeat KVP? You said it was the...
So KVP, its purpose is to penetrate the patient. Okay? Therefore, it is the beam quality. Right? So its purpose is to penetrate through the body, and it's also considered to be the beam quality. So MAS is what? The quantity of what? Photons or electrons. And KVP is what? All about penetrability, and it's also the beam what? Quality. So both, they have their purpose.
So MAS is the quantity?
Quantity, yes, quantity of photons or quantity of electrons that we need to create BRAMPs. Yes, sir.
My question is, I know that they all work together, MA, KVP, but would it be correct to say that the mask has a direct determination of the contrast?
So are you talking about, okay, so with digital, I would say it has something to do with window width and window level, if we're talking about digital. But if we were talking about like CR and DR back then, it would be density, right? But the KVP does play a huge role in the contrast. Yes, it does. Yes, it does. And I'll cover that next week too. Okay. Any questions about the long wavelength and stuff? Yes, ma'am.
Just, what's the 15%?
Oh, I was about to go there, girl. Okay. So 15% rule. I need you to understand the concept. If I give you a math, I think I'll be overwhelming you guys. But the math part is easy. It's the concept that matter. So 15% rule tells you that if I shot the first X-ray and I said, hey, I want more contrast. Definition of contrast is the shades of gray. We always want a wide latitude. Wide latitude means between black and white, I have many shades of gray, right? If I have a narrow latitude or a high contrast, I have black and white. I don't want that, right? I want many shades of gray. So the 15% rule tells you, if I went ahead and I shot a first picture. The picture I shot, let's say a chest x-ray. Nah, I give you a hip. For a hip, I use 75 on myself, 75 at 50, okay? So let me write this down real quick so it makes sense actually. Where's 75 by 50. So if you ever hear 75 by 50, so 75 kVp at 50 mass. That was the first picture that I shot. And I'm like, wait a minute, I have high contrast, meaning I got too many what? Black and white. I want many shades of gray. 15% roots is telling you, because kVp controls contrast or the beam quality, I can go ahead and decrease my kVp by 15% and increase my mass by half of it. Meaning half of 50 is what? 25. 25 plus 50 is what? 75. So now the next picture that I shoot, this will be my tech factor, which I believe is like, what is 50% of 75? I think it's like 60.
12.5.
12.5. So 12.5, that's like 63-ish, 60 kVp. So my new tech factor would be 63 kVp at 75 mass. Just so I could get more shades of gray. It's the concept that is behind it. And we use this very often because patient body habitus, if you're not good with tech factor, you're going to have to repeat. And if you're repeating, you need to know how to do it. And majority of the time, we use what we call the 15% rule. It's depending on which tech factor, I need to kind of like adjust. If I go down by 15%, I need to increase or decrease the other tech factor by 50%. That is the concept behind it. Math, I won't do you guys dirty. But the concept matters to me. Okay? And I think your book even explains it even further. Yes, sir.
Have you ever done that conversion more than once? It's like if you dropped it 15%,
Mhm.
wasn't enough and you had to do it again?
You mean I did it the first time and then I did it the second time and I have to do it the third time? No. If you have to shoot it the third time, you really got to get somebody else that's more experienced at this point. Yeah. That's just you not knowing your tech factor, right? But there are other ways around it. But definitely, if you're supposed to repeat. I personally think you should only repeat once. But everybody works differently, right? But the 15% rule, I think Olivia, she said she used it before. Hector have used it before. I used it a couple of times myself, right? And the concept is what? If I dropped a certain tech factor by 15%, I need to increase the other tech factor or decrease the other tech factor by 50%. But mostly we do this with KVP, okay? Not mass, KVP. And I think this is what it tells you here too. Yeah, go ahead.
So when you did the whole example of the 75 at 50,
Mhm.
you always, if you decrease, you increase the other side.
Yes, exactly.
Reverses.
It reverses, yeah.
And it has to be 15% of both.
No. So every time I decrease my KVP by 15%, I have to increase my mass by 50%.
Oh, 50%.
50%. Just think of it as that. Okay? And this is really related to KVP. The 15% rule is really related to KVP. When I increase or decrease my KVP by what? 15%, I have to also increase or decrease my mass by 50%. That is the concept. Okay?
15%
50, exactly. 50% on the MAS. Okay, so let's talk a little bit about SID, the inverse square law. So the inverse square law tells you that intensity decreases as the distance increases. That's inversely related to each other. And the intensity will always decrease by 1/4. Okay? I have to give you a homework on this, and I'll go over it next week before lecture, so we can solve more of it. But then the concept behind it is that the intensity of the X-ray beam decreases as distance increases. Okay? The intensity of X-ray or the intensity of the photon decreases as the distance increases. For example, so let's say you were standing, and I got damn, I don't know if this will work, but I'm gonna need you again. I'm so sorry, I keep bugging you. Stand right here for me. I've never done this, so bear with me. I hope it works. Face me. Okay. Actually, back up a little bit. Okay. So I have my flashlight, right? Hold on. We don't have to dim the whole light. Let me dim the whole light real quick. I'm not sure if it will work, but turn on. Yeah, I don't know how to turn that one off either. Maybe it just stays on.
Why don't you stand over there?
Yeah. Well, they
Well,
will
you
see
got
me.
the lights.
Yeah. Oh, hold on. Damn. Let's go in the dark a little more. Get closer to me. Right here. Right there. That's good. Okay. So the closer I am to him, is the intensity not a lot greater, meaning the brightness of the light is not greater. The further I go, you don't see the light anymore. That's what it's telling you. The light is the intensity of it. So the closer I get to the X-ray tube, the higher the intensity. The further I go, the less the intensity between me and the X-ray tube. Thank you. Does it make sense?
Yeah.
Okay.
Longer distance equals less intensity.
Less intensity,
Short
but
distance.
greater intensity. So it's inversely related. But if we're talking about in the math aspect, the intensity would decrease by 1/4. Okay? So the closer I am, the higher the intensity. The further I am back, that is twice the distance, is going to be 1/4. The intensity would decrease. Okay? You need to understand the concept, not so much of the math. Okay? Okay. So yes, this is the formula for it. This formula you would need it for every program you go to. It is even a board exam question. You just need to memorize it. There's another way to write it. I wrote it over there. I will show it to you after I bring this up over there. So then we have what we call exposure maintenance formula or density maintenance formula. It's the same interchangeable. Okay, so what happens? What is this formula is telling you that mass is directly related to what? The patient, and it's directly related to also the distance. D is for distance. So what that means is the further I go away from the image receptor, the more tech factor or the more mass I need for it to reach what? The image receptor. So this is directly related to each other. The inverse square law is inversely related to each other. Do you understand what I mean by inversely and directly?
Inverse are like opposites.
Are opposite. That means when one goes up, the opposite goes down. Directly means when one goes up, the other one goes up too. Are we clear? Because you're going to be hearing me saying inversely, directly throughout the whole class. And I need you to understand that. Okay? So this is telling you that so if this is the X-ray tube here, the further I go back here, I need more mass to reach me. The closer I get, less mass I need to reach me. Is that concept okay? So if I ask you to write it, you gonna be okay? Huh? Explain it in an essay?
So, for the other equation,
Mhm.
it was the closer you are to the X-ray beam, the higher the intensity.
Yes.
For this one, it's the opposite.
It's the opposite. That's why the other one is called inverse and this is called direct. They both do different things. This particular formula is directly related to image. And this is why I have this here. So this X-ray, you are supposed to shoot this X-ray at 40 or 42 SID or 48 SID, meaning the distance, right? That is the SID that I'm supposed to shoot it at. Now, some technologists would forget to change their tech factor, and they will burn their image. This is the burnt up image, and this is the image that is not burnt up because they used too much dose here, and they used optimal tech factor over here. And you guys probably don't see the difference, but this is the burnt out one, and this is the non-burnt out. Yes, sir.
The difference in the detail?
Difference in detail. Yeah, you could say that. Yeah, definitely. Because the mass controls what? It controls the amount of photon that are reaching the cassette, right? So the closer I get, I don't need that much dose compared to as if I ever went further. And when you're with this kind of exam, you will have to go from 40 to 72 or 72 to 40. Some techs forget to change their tech factors, and we end up getting these kind of pictures. Okay? Any questions so far? Okay, moving on. Almost done. Oh, half value layer. Oh, shit. Sorry.
Can't go back.
I can't. It's recording. I can't go back. But it's okay. I'll talk about half value layer. Half value layer, we are measuring the thickness of the material that is going to decrease what? Photon. Okay? The thickness of the material that would decrease photon, which is associated to attenuation. Okay? Yes, ma'am.
Sorry, can you repeat that one more time?
Half value layer is measuring the thickness of any material that can slow down the intensity of photon or just photon itself. That is the simplest layman terms I could put half value layer. Okay? We are measuring the thickness of the specific material that we can place in the beam's path to slow it down or cut it by half. That's why we call it half value layer. The thickness of the material that we can place in the beam's path to decrease the intensity by 50%. The most common material we use is aluminum. Okay? And when I cover the X-ray tube, you will notice I would talk about filtration, because filtration material is an object or something that we use to remove certain kind of photons and so forth. So I'll cover that next week too. Okay? Scatter radiation. Scatter radiation occurs because of what? The patient. That's why I end up getting my dose. So as Bremselaar comes out of the X-ray tube, reaching out the patient, guess what? There are some wavelengths that are so long that they're not hard enough to penetrate through the patient, and therefore we get what we call scatter. That scatter interaction alone, I will cover it next week. Okay? How do we control the scatter radiation? We can control the scatter radiation based on what we call beam restrictions, which is associated with what we call collimation. Collimation is if you've been into an X-ray room, you know how they turn the X-ray through. There's like a light facing you or something. That light is called collimation. The reason why we have collimation or that light in the box is so that we can only cone down to the area of interest. If we open it up, that means we are exposing unnecessary structures. Therefore, we can restrict the beam to the anatomy of interest, and we can slow down or limit the amount of scatter that gets out of the patient. Okay? Then we have beam filtration. As I told you, the filtration, we apply filtration to remove, hear me out, I'm about to use another terminology, soft photons. Soft photons are also considered as long wavelength, low energy. All these are interchangeable terminology. Soft photons are known as low wavelength or wide wavelength, okay? And low energy. All these are interchangeable, okay? Let's talk about grids. So grids is actually associated under the table or on the wall bucket, or we can also use it for portable or tabletop. The whole purpose of a grid is to limit or reduce the amount of scatter that are reaching the IR. Okay, that's the definition I need to focus on. Grid, it is an object that we use to decrease the amount of scatter that are reaching the IR. Because remember, the scatter didn't penetrate the patient. Just because it didn't penetrate the patient doesn't mean that it's going to just disappear. It can reach the cassette For us to remove that, we place what we call grid. We eliminate what we call fog, unwanted information on the cassette. Okay? So what's the purpose of a grid? To remove or reduce the amount of scatter that's going to be on the image receptor. Any questions? Okay. This is more of a I'm not going to cover so much of the grid stuff, but I'll just touch a little bit on it. So the grid is structured in a specific way for it to be able to eliminate or reduce the amount of scatter. We have a whole math on how we dictate what kind of grid we have. I'm not going to get into it, but that's all I want you guys to know, okay? So let's talk about image contrast. Image contrast is the difference of shades of gray on an image, okay? Image contrast. So once the image is being processed, it goes through what we call a histogram, which is related to the DR, CR, and so forth, and I'm not covering it. But just know the contrast allow us to see, or it enhance the visibility of the detail of the structure. So it's detailing of the structure that we are trying to see. So this is extremely, extremely important. Okay, when we talk about high contrast, I think I explained it earlier. High contrast means we have short scale. Short scale means I have more black and white than I have of shades of gray. Okay, so high contrast means I have short scale, meaning I have a very narrow latitude. Means I have more black and white than I have of shades of gray. I always want more shades of gray than just black and white. If I have, let's say I have 100 to 1, okay? Between 100 to 1, from 99 to 2, I want everything to be shades of gray, okay? So I want that. That's how we are able to get optimal image quality, okay? So when we have low contrast, that's what we want. Low contrast means I have wide latitude and shades of gray, okay? That's what we want, wide latitude, shades of gray. And we call that window width. In digital radiography, window width means contrast. Brightness, okay, brightness is what we used to call density in film. But when we talk about brightness, we're talking about the density of the image. When we talk about window width, we are talking about the contrast of the image, okay? These terminology are going to be going around a lot. So yes, I didn't shoot this picture, by the way. But I wanted to kind of like give you guys an idea of how KVP and mask can actually affect the picture. So I should notice there's too much what? There's too much mass here, and we have less KVP, and this picture is not good. Look at this. They burnt out the patient and even increased the KVP even higher. You don't want this, okay? So this is all the text factor being combined to produce an image, okay? So if you have a high KVP, that's okay, but your mass got to be low. You can't have a high mass and have a high KVP. When you have a high KVP and you have a high mass, what you're telling your X-ray tube is you're telling the KVP to push all those mass towards the patient. Therefore, I always want low mass, high KVP, so that I could get this kind of picture. You see that? High KVP, low mass, to get an optimal image. Then we have what we call subject contrast. This is really related to digital. Once you shoot a picture on the digital equipment, it kind of like, there's like a huge lag from when you exposed it to when it shows up. This will pop up on your screen. This is how the picture is as you shot it. But because we have digital, we got different tools to kind of like polish the picture. This is how your picture will end up more detailed. Okay? So this is the raw image, and this is the display image contrast. This is what you send to the doctor for them to see. Look at how detailed that is compared to that. Super detailed. This is super way detailed compared to that. I mean, look at how sharp. Look at the edges. Super detailed, super sharp. There's no sharpness around there, none of that. Okay, yes, ma'am.
So being a rad tech is really just
Don't say just, because that's going to break my heart.
well, it's not just aside from just taking a picture, but the quality.
Oh, God, quality matters. And the quality actually comes, so there are two, I always say there are two types of quality: positioning quality and tech factor quality. That's what, apart from patient care, that's what matters. Like, it's so huge. If this picture was burnt out, ain't no way in hell I'm going to send that picture to the radiologist. No way. They'll call you back and tell you to repeat it. When it's burnt out, you know what that means? You have overexposed the patient. Why would I want to re-expose the patient again when I have already overexposed them? Because the first one that you shot was not good enough. And you burnt them out. And now you got to lower the dose that you could have done the first time if you knew what you were doing.
So
Right?
there are technicians that mess up like that.
Hell yeah, they're everywhere. We everywhere. I mess up sometimes too. I'm not ashamed of that. And I mess up when I'm lazy. And I mess up when I use what we call AEC. That's something that you learn in the program. AEC is a tech factor, but what happens is the system has already give you the average tech factor of a patient. And if you don't turn off the AEC, it can burn the patient. The average tech factor is telling you it doesn't matter if the patient is big or small. Use the same for everybody. And remember what I said, I wouldn't use the same tech factor on him, on me. You should never do that. But AEC, it's like a part of the X-ray equipment that allows technologists to be lazy. And I hate that. So me, I turn it off. I say 95%, I turn them off. And I set my own tech factor. Knowing your tech factor goes a long way. That's what's going to make you look like a good tech, even if you're not. Tech factors matter. Because remember, you are prescribing the dose, radiation dose to a patient. You are prescribing it. Right? So you have to be very careful how you set up your tech factors and so forth. Okay? All right.